Okay, yeah, I think we can start. So let me just remind you briefly where we ended yesterday. Let's see. Okay, so what I was telling you yesterday is that we had already talked about the Legendre polynomials, but there are a second type of second family of polynomials called the Chebyshev polynomials, which are also very useful. We'll talk more about why they're useful tomorrow, but at least I'll kind of like just finish saying like the main properties that they have today. So again, like I'll just kind of like write the very first ones to have them as written down somewhere. So the degree zero Chebyshev polynomial is 1. The degree 1 Chebyshev polynomial is x. The degree 2 Chebyshev polynomial is 2x squared minus 1. The degree 3 Chebyshev polynomial is 4x cubed minus 3x. And for example, the degree 4 Chebyshev polynomial is 8x to the 4 minus 8x squared plus 1. And let me do one more. The degree 5 Chebyshev polynomial is 16x to the 5 minus 20x cubed plus 5x. Um, and if I just had started writing them down like that yesterday, then it kind of like looks mysterious where they're coming from. What I was mentioning yesterday is that one way, like a very convenient way to think about these polynomials is that if you have the interval -1 to 1, which again is like you know, it's basically where we're studying everything as of now. If you have the interval from -1 to 1, you can look at the top half of the unit circle, right? Where like, x squared plus y squared equals 1. And because of like polar coordinates, you know, if you use polar coordinates because the unit circle has like radius 1, then you can say here that x is cosine of theta. So if you use the fact that x is cosine of theta, then you can rewrite this in terms of theta, and in terms of theta, they look a lot more transparent. So in terms of theta, this just becomes 1, this becomes cosine of theta. Of course, that requires playing a little bit with the trig identities, which is what, I was trying to show you yesterday. But like the formula becomes like very, very elegant. And so in general, it's kind of like easier to say what the formula is in terms of the angle theta. So the formula for in terms of the angle theta, um, you know, is like cosine of n theta. And in terms of x, like you can use this like although it looks a little bit weird to write it like this, but like that's how people would usually write it because then theta becomes our cosine of x, right? So you can write it like in terms of x. If you wanted like a formula in terms of x, this is how you would write it. Although it's not like very illuminating, it looks a little bit confusing. But and if you had just started by writing it this way, um, if you had started by writing it this way, like it wouldn't have been clear at all that you end up getting a polynomial or anything like that. So, but that is kind of like how like these Chebyshev polynomials are found. Um, and again, I'll tell you tomorrow. Tomorrow we'll talk about why they're useful, um, like for numerical analysis. Right now, I'm just kind of like introducing them. The last thing I want to mention about them for our purposes, in terms of properties, is that one of the other nice features that you have is that they are orthogonal. Like that's what I was trying to say yesterday. Is in terms of the variable theta, the polynomials are orthogonal. So you can think about it as a fact. So in terms of theta, the different polynomials are orthogonal. Orthogonal in the sense that like like the theta, the angle theta runs from 0 to pi here because it's like the top half of the circle. So what I'm saying is that if you were to integrate any of these two polynomials, if you did the integral from 0 to pi of one of these polynomials times the other polynomial with respect to theta, this gives you 0 whenever n and m are two different in polynomials. So this is 0 whenever n is different than m. So for example, what I'm saying is that for example, the integral of cosine of 2 theta times cosine of 3 theta is 0, or like the integral of cosine of theta, cosine of 4 theta is 0. More generally, I mean, again, this is just like the way to do this is because there are a bunch of trigonometric identities that relate, um, you know, oh, sorry, I should put the theta because I'm integrating with respect to theta. There are a bunch of trigonometric identities that always relate how to multiply two cosines or two sines and things like that. So if you were to go through all the details, you would find that these integrals are always 0. At least whenever like the number multiplying the integers multiplying theta are distinct whenever n is different from m. And the reason why that's useful is that if that is how like that this so I'm saying these integrals are 0 in terms of theta, and if you do a change of variables, like kind of like literally this is just like a cal1 change of variables, right? Um, which is kind of what I was trying to do at the end of like yesterday's class. Then if you use like a change of variables using kind of like a U sub, actually. It's like a U sub that x equals cosine of theta. So dx is negative sine of theta d theta, or so dx is minus what is sine? Sine is 1 minus cosine square of theta d theta. And then that gives you that dx is minus root of 1 minus x squared d theta. Then you can kind of like this is kind of what I was doing towards the end of yesterday's class. Like you can just do all of this work, if you wanted to see these integrals in terms of theta. And so what if you kind of like do this, rewrite the integrals in terms of x, sorry, if you rewrite the integrals instead of in terms of x instead of theta, you find after doing some work in terms of x, you find that this you find that then like the integral from -1 to 1 of Tn of x times Tm of x times dx over root of 1 minus x squared equals 0. So the reason why I'm bringing this up is that basically what that means is that in terms of the x variables, the polynomials are orthogonal, but not with respect to the inner product that I mentioned. That's like at the beginning of when we started talking about inner products. There's kind of like a distortion that happened. So it's kind of like a distorted inner product. I mean, no one uses like the word distorted, like they just call them weighted. So like what this is saying is that in terms of x, that Chebyshev polynomials are orthogonal, but with respect to what people call like a weighted inner product, which we won't be using too much, but it's kind of like a useful thing to at least bring up so that you kind of like know that it does happen. Uh, the polynomials are orthogonal with respect to what's called like a weighted inner product. To weighted inner product. Okay. So it's kind of like, a weighted inner product. Essentially, what it does is kind of like distort your. If you remember in Calc 3, when you do like a change of variables with this Jacobian business, kind of like the grid gets distorted. And so kind of like it changes like the notion of perpendicularity in a sense. So kind of like the idea is that if you kind of like change your mind about what it means to be orthogonal or perpendicular, then with respect to this notion of being perpendicular, then these polynomials are still perpendicular. But there, again, we're not going to use directly this weighted inner product. Um, but what the reason why it's useful to know that they are orthogonal, even in this distorted sense, is that once you have functions that are orthogonal, either in the traditional way or the distorted sense, they are linearly independent. Okay, so that like these fact guarantees that the Chebyshev polynomials are linearly independent in the same way which in differential equations, when you were talking about solutions, you would talk about whether functions were linearly independent of one another. So what that means is that any polynomial of degree n will be a linear combination of Chebyshev polynomials. So that is kind of like the useful fact. So from here, and that's the only thing that I'll use. So from here, from this fact, one can conclude that every polynomial um, of degree n is a linear combination of Chebyshev polynomials. I'm about to do an example to show you what I mean by that. Is that making sense? Like questions up to this point? So here's an example. Here's an example. Let's take a polynomial of degree 2 just to make it easier, like a parabola. Okay, let's take a parabola. And I'll do it, I'll make it x3 minus x plus x squared. Okay? So this is a degree 2 polynomial, right? So this is a degree 2 polynomial. So what I'm saying is that because it's degree 2, the previous fact that I just mentioned means that this polynomial can be expressed as a linear combination of the Chebyshev polynomials up to degree 2. So P2 of x is a linear combination of t0x, t1 of x, and t2 of x. Okay? So what does that mean in practice? So what that means in practice is that p2 of x is a constant c0 times t0 of x plus a constant times t1 of x plus a constant times t2 of x. Okay? So, I mean, again, like this is similar to maybe what you did in differential equations, where you were talking about solutions to a linear differential equation, which was a linear combination of like a basic set of solutions to the ODE. Um, and then you could check independence of the solutions and things like that using the Wronskian and other stuff. I mean, we're going to do it slightly more simple ways, but it's kind of like a similar idea. So in this case, what was the polynomial? It was 3 minus x plus x squared. Then C0, okay, then C0, what is T0? T0 was 1, right? Then you have C1, what is T1? T1 was X. And what is T2? T2 would be 2x squared minus 1, right? So what happens at this point is, I mean, you kind of like rearrange terms a little bit so that organize them by the powers of x. So let me just put it like this. This would give you this. So what do you get without an x? The thing that you get without an x is C0. This has no x, and this one has no x, so you get C0 minus C2. Then let's look at what has an x. Oh, the only thing that has an x here is this one, right? So let's just put it as C1x. And then what has an x squared? The only thing that has an x squared is the last one, right? So you get 2C2 x squared. Is that okay? Is that making sense so far, so good? And then it's like a simple system of equations that you have to solve, because the only way for two polynomials to agree is like for infinitely many values, because they have to agree at all the points between -1 and 1. So that gives you infinitely many points to agree on. And two polynomials cannot agree on infinitely many points unless they're exactly the same polynomial. So that forces the coefficients to be the same. So that gives you a system of equations. So if you equate the first coefficients, that gives you the three gives you the 3 equals C0 minus C2. If you equate the second coefficients, that gives you that -1 equals C1. And if you equate the last coefficients, that gives you that 1, that gives you that 1 equals to C2. Okay, and I kind of did it on purpose so that it would be a simple system to solve. But that gives you that C2 equals 1/2, right? And then you already have the value for C1 here. And then you get that C0 equals 3 plus 1/2, right? And that is 7/2. Okay. So what that's saying, and you can double check it, but what that is saying is that then 3 minus x plus x squared would be C0. C0 is 7/2 times the first Chebyshev polynomial plus C1. C1 is -1. So let's put here -1 times the second, I mean, the Chebyshev polynomial of degree 1 now, plus 1/2 times the Chebyshev polynomial of degree 2. Okay, which was 2x squared minus 1. So again, this is T0, this is T1, and this is T2. And Any polynomial of degree n will be a linear combination of Chebyshev polynomials because of this fact. And so I'll give you, I'll add some more problems today on the PDF guide. So like, I'll put some of these for you to work it out. But that's kind of like the idea in general. This will be useful again between today and tomorrow because we will have to do Lagrange interpolation very soon. Um, and it will be useful to express after, it will be useful when we do the Lagrange interpolation to express a polynomial that you get after you interpolate in terms of the Chebyshev polynomials. And you'll see why that's useful. Like, again, we'll talk about that between today and tomorrow. So that's where kind of like everything will start kind of like coming back to like blending in. Is that okay? Is that making sense so far? So good questions up to this point. Okay, so the next thing that I'm going to tell you for today is actually to start talking a little bit about how this stuff that we have been discussing is related to approximating to estimating derivatives. So again, in numerical analysis, basically the whole point is to develop numerical methods or approximation methods for many things that you already know how to do theoretically, like finding derivatives, taking integrals, etc., etc. So there are like kind of like approximation schemes for finding derivatives, and that is kind of like what I was going to tell you about today and how that's related to this stuff that we have been doing with polynomials. So there is actually a connection, which is kind of like nice. But before that, I just wanted to mention some notation, which is actually useful to know outside of this class, which is the Landau big O notation. I don't know if I imagine some of you have seen that one before, but it's like a small detour, but that's convenient to have, like, as a mental idea. So, especially in computer science, and many other places, you will see this notation used a lot of the time. So it's kind of like useful to like to know how it's used. So I'll kind of like give you like a you know like kind of like an explanation, like a intuitive explanation of how people use it, which will be more than enough for our purposes. But of course, as always, there's always like a formal definition if you wanted one. But we don't need to have like we just need to know like kind of what it means um, on an intuitive sense to kind of like have like some advantage with it. So let me start with an example. I'll do two examples actually of how the Landau notation, like the big O notation, can be used. So here's like example one. Okay, let's say that A is a non-zero number. So say A is a non-zero number. Okay, so what is and H is like any number, right? And H is also like a small, and H is any number. Which in a moment we'll think about it as being small, but for now it can be any number. Okay. So what is A plus H squared? Okay, there's not something um you know that that is something that you have done all the time. So what is A plus H squared? That's A squared plus 2AH plus H squared, right? Okay, so that's not too bad, right? And then if you subtract A squared on both sides, you would get that A plus H squared minus A squared, right, is 2AH plus H squared. Is that okay? Is that making sense so far, so good? Now, uh, as I said, like so far, um, you know, I don't know anything specific about age, right? But kind of like in calculus, like the reason why I'm using h is because hopefully that reminds you of the limit notation, right? So like in calculus, like I'll write it in a moment, like the limit notation for like the derivative at a point was something like this, right? So in calculus, you would think of h as being like really, really small, right? So now now let's suppose that now let's think about that h is very small. So now we think of h as being very small. What does it mean to be small? Like in this case, it kind of like means that like implicitly that you're going to be taking kind of like a limit as h goes to zero. That's kind of what you want to think about it as being small. In particular, that also means that eventually h would be less than one, right? Because like that is kind of like you're kind of like decreasing the value for h considerably. So once like you make h really, really small, right? Okay, maybe I should ask this as a question. If h is super small, right? If h is super small, of these two terms, which one should be, no, which one is the smaller one of these two terms? If h is super, super small, which one seems smaller to you? In fact, we can put like a particular number value for a so that we don't get confused with a. So let's say that a had been 4. So that gives you that 4 plus h squared minus 4 squared, right? Would be what? If a is 4, that gives you 8h plus h squared. Maybe that makes it easier, to kind of like see what's going on. So between these two quantities, right? Between these two quantities, which one is the smaller one? Um, which one is the smaller one as h becomes like really, really small? You can even think numerically as putting like giving values to h. So you could think about it as, yeah, exactly, right? Like h, once h in fact gets like less than 1, right? When you start squaring a number less than 1, the square becomes even smaller, right? So what that means is that once h is really, really small, like this term kind of like becomes insignificant with respect to the linear term. So in this case, the quadratic term. Well, I mean, you could use the word negligible also. Um, I'm sorry, you just give me a second. Like it can be, like what I mean by that is it can kind of like be ignored for all numerical purposes with respect to the linear term. So kind of like in the big O notation, right? In the big O notation, what you would write is that you would write something like this. You would write that 4 4 plus h squared minus 4 squared is big O. That's like where the big O comes in. You would write something like big. This is not like a zero. It's kind of like a big O, uppercase O. So you would write like big O of h. Now it looks more like a zero. Well, I think sometimes they kind of like do it kind of like a fancy curly O. Um, it's like a big O of h, and by that they just mean to say that the relevant term, you know, if you were to simplify this, the relevant term depends on h. Like the dominant term involves like an H. Okay, so this is what it means here. So here, this means well, and here for H small, right? Like for H small. The dominant term. Is that making sense? Um, okay, so let's continue with this example so that you see that like an interesting difference, and then I'll do another one. So let's continue with this one. But now let's say that I tell you that H is large, right? Like, so now you're thinking of H as being large. So now H, now, so again, like that corresponds to kind of like pictorially, what you can have in mind is that you're thinking that H is going to infinity, right? So H will be 100 and then 1,000 and then 1,000,000 and then 1,000,000,000,000 or whatever you want, right? So if H is now getting large, right, of the two terms, right, of the two terms, the one that dominates, right, like the one that is the most important one to take to care about, right, the one that dominates is H squared, right? So now this one is the dominant term. Is that making sense? So in the big O notation, now you would say that this is O of H squared for H large. So you would say that 4 plus uh, 4 plus H squared minus 4 squared is big O of H squared for H large. So when you say big O, you just what you're trying to say is that which is the dominant term, uh, like which is the term that matters most, like when you have like an expression. Is that making sense? Kind of like here's another example, which is like a very useful one, and this is actually one of the things that are very important in whenever you're thinking about algorithms and like computer science and applications, like when you're approximating things. So one very useful question is like how much time does it take to multiply matrices? So you could ask how many operations are needed to find the product of two matrices. So here's let's do that in one because it's like actually like a very interesting example. Um, and like the way people will refer this is like what is the cost of matrix multiplication? Okay. So let me just do it for like the 2 by 2 case just to make it easier. But let's say you have two by two matrices, right? I mean, I won't even like think too much about the names. I'll call them A1, B1, C1, D1, and you're multiplying that by another 2 by 2 matrix, which is A2, B2, C2, D2. Okay, so this is a 2 by 2 matrix, and this is a 2 by 2 matrix. Okay. So as you hopefully remember, like the product of two by two matrices is going to be 2 by 2, right? And what do the entries are of this 2 by 2 matrix? So you kind of like do these with this, like right, like the dot product. So the first entry would be A1, A2 plus B1, C2. Then you do this one with this one, right? And that's the second entry. So you do A1, B2 plus B1, D2. And then this one with this one, you get C1, A2 plus D1, C2, right? And the last one, this one, oops, this one with this one, you get C1, B2 plus D1, D2. Is that okay? That is, those are the entries for multi of like the end result of multiplying two by two matrices. Okay. Um, and like, if you are if you're putting like some, like, now you could, like, of course, what I want us to think in a moment is like, what if the matrices had been like two 100 times 100 matrices, right, or things like that. But for now we're kind of like starting slow. You'll see what the answer should be in that case very quickly. But kind of like the idea is that if you think about it from like a computer perspective, literally the only thing that the computer will do is kind of like arithmetic operations, like multiplications, additions, like in binary. Okay, so you can, when you ask what is the cost of matrix multiplication in a very naive way, ignoring many other factors, like, but kind of like the more like straightforward answer you could give is like, how many arithmetic operations does doing the matrix multiplication take you? So my question is like, how many arithmetic operations were needed? And by arithmetic, I mean like multiplications and additions, if you want, right? Um, okay, so maybe if someone wants to do the count for me, how many multiplications can you see? Like in total, how many multiplications were done in this process? They were eight multiplications, good. And how many sums were they done? Like how many sums are there? There are only what? Four, right? Four additions. Okay. Oh, and what is eight? Eight is two cubed, right? Two cubed. And what is four? Four is two squared. Of course, like this is not a proof, but like hopefully it can kind of like become I mean, you could convince yourself, like, it's a kind of good exercise to think about it in the way I'm doing it. If you had like two n by n matrices, where this is n by n, and the result is something that's n by n, that actually takes n cubed multiplications and n squared sums. Okay. Um, It's not okay so far so good. So kind of like in terms of like multiplications and additions, that's kind of like the cost, like the naive cost, because like again, it's kind of like the most straightforward way to try to do the multiplication, the way you learn it in the first linear algebra course. That's like the most straightforward way of doing the multiplication of two matrices. So again, if you thought about like trying to measure how much effort is being spent in multiplying two matrices, first, like, it's not true that multiplication and addition are equally easy, right? Like, multiplying numbers is harder than adding them, right? But even if you kind of like assume that they are equally hard, which there is not the case, but even if you assume that they're equally hard, like, you can see that they are like over, like, there are more multiplications needed than additions, right? Like, even if you pretend that they are like the same effort. So in the big O notation, what you would say is that matrix multiplication, requires O n cube operations, because once like n is large, like well, not even when n is large, but obviously you only care about this when n is large. Like the dominant term of these two expressions is n cubed. So you would say, like, usually when you say when you talk about the cost of matrix multiplication, you would just say is O of n cubed. So the cost of matrix multiplication. Is that making sense? Kind of. So, like, again, if that means that if n were like 100, right, like two 100 times 100 matrices, that then it is what 100 cube uh, number of operations roughly which you're expecting, because 100, because once if you're comparing 100 squared versus 100 cube, 100 cube is the dominant term, and that even just gets worse, or like more like a more of significant difference as n gets larger and larger. Okay. And so like it's useful when that, like if we were to get more into the weeds of a lot of these numerical analysis, you could like ask a lot of these questions, like how many operations does it take to implement the algorithms or things like that. Like what's kind of like cool in this particular case uh, is that there is an alternative way of doing the matrix multiplication that requires fewer operations. So that's called like Strassen's algorithm. I'll just mention it because like it's an interesting thing. Where roughly you can make the cost like O of n 2.181. You can multiply matrices in a different way, in a more efficient way. That has cost roughly. I mean, it's an approximation, and I think they're a little bit better bounds than that one, or more efficient ones. Because the idea is like like that may not seem like a big difference, but like when you have to compare like 10,000 cube versus you know 10,000 to the 2.81, that is a difference. And like the bigger the matrix is, the more the difference would be. So any improvement that you can get on the cost can be like really, really, really useful. In fact, I believe like there was a kind of like recently, I don't know, one of these like large language models like Claude or one of those kind of like found like another way of doing the matrix multiplication which no one had like found before. And I don't know how efficient it is compared to these ones, but like I'm just saying, like in a lot of numerical analysis, just like doing a slight improvement in the bounds, like in the cost, can be like tremendously important, because again, when you're dealing with large numbers, like anything kind of like helps. So but yeah, it's like, so like this terminology of big O notation is super useful to understand, because it is like a very quick way of talking to someone. When you ask them, oh, how expensive this is, like how much time does it take, what is the dominant term? So having the big O notation around, it's just like a very easy way to kind of like communicate with someone else, like um so you so yeah, like this is a good, like I wanted to bring it up because now we're going to talk about how to estimate derivatives. And when you do that, it's useful to have like this O notation around, and then we'll see how that is related. Estimating derivatives is related to polynomials, although I may do that tomorrow. Um, but yeah, like the estimating derivatives part. it's a slightly different topic, so I think it's like a good. Let's just do like a quick 5 minute break in case someone wants to ask me anything else about this. And if not, I'll start telling you how to like how the estimation of derivatives works. So let's say 11:22. Um, okay, so yeah, let's talk a little bit about derivatives today, and tomorrow we'll wrap up this topic. So this is sometimes called like finite differences. It's also called, I mean, it's also related to something that's called spectral methods, but I'll maybe tell you a little bit more about tomorrow. But the idea is kind of how to like estimate like the derivative of a function at a particular point. Okay. And okay. And so the, you know, first, like you could just like start by what was the, what was the definition of the derivative, right? Like if you remember, like in terms like the limit definition of the derivative at a point, right? What was f prime of a? I kind of like wrote it for a second before erasing it, but f prime of a is f of a plus h minus f of a divided by h, right? So that's a limit definition of the derivative. Now, be, from Calc 2, one of the things the you learn from Calc 2 is Taylor's formula, okay? Which is kind of like a more explicit way to think about the function. Sorry, like all these calculations. So what Taylor's formula say is that f of a plus h is f of a plus um, f prime of a times h plus one half. I'll kind of like write what I need for today. So I'll just kind of like write like the relevant terms for my purposes. So before I would just have kept writing dot 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 dot, right? But now that we have like this O notation, I'll write big O of H4. Okay. Um, and by that I just mean that again, because here we want to think of H being small. So here for H small. So that just means is like the next term that matters, like the dominant term of all the junk that's left is like it's dominated by h to the 4. That's kind of what it's saying. Again, and there's like a more precise like estimate you could give if you wanted to, but like for my purposes, that's fine. Okay, so if you just play around with this formula a little bit and rearrange terms, right, from Taylor's formula, you can say that. Um, you know, so just rearrange some things. And so you would get that f of a plus h minus f of a, right? And gives you f prime of a h plus 1/2 f double prime plus 1/6 f triple prime of a h cubed plus o h to the 4. Okay. And now everything on the right hand side, has at least an h. So if you divide everything by h, you get that fa plus h minus f of a divided by h is f prime of a plus 1/2 f double prime of a times h, right? Because now I divided by h, so there's a fewer h not everywhere. And if you divide by h, then the O of h4 becomes O of h cubed, okay? Is that okay so far, so good? Is that making sense? Okay, so the first way to, and this is almost like the linear approximation. Like this is not something new. This is something that you know from Calc 1 even. But the first way to approximate the derivative, and this is called like the forwards difference approximation. Oh, let me write it down. Is to say that the derivative, is like it's just saying is, you know, if you solve for f prime of a here, you can say that the derivative is f of a plus h minus f of a divided by h, and all this junk is like, again, if h is small, all this junk is O of h actually, if you thought about it as a single quantity, you know. So by the way, it doesn't matter, like, you could say, oh, isn't it minus O of H? Like, like you never put a kind of like a constant in front of the O of H's. So you just say like you never write 2 times O of H or minus O of H. Like that is because O of H just means whatever is there depends on H. So you don't really care about the coefficient. So I'll put some problems also so that you kind of like get used to this big O notation. But all that I'm saying is that like in the forwards difference approximation, uh and this is kind of like basically like the linear approximation. You might as well call it that because like it's not that different from what you would have done in Calc 1. The only thing is like the only difference is that it's giving you a little bit more detail in what that, like, by how much the error is, because it's saying, you know if you use this approximation for the derivative, the difference with the true value depends on h. That's basically the only, you know, the only difference here. So this is an approximation to the derivative um, with error term, which is O of h. Okay. Is that making sense? Kind of like how I got it. Of course, like in practice, like the way you would use it is you just give h as a small value, like 0.0001 or whatever, and then you just like plug it in for that value, and that's kind of like the approximation to the derivative that you would use, right? So like like as an example, if a is 0 and f of x is cosine of x, according to this approximation scheme. And let's say that h is 0.001. According to this scheme, what is f prime of 0? It would be f of, or like, well, cosine of 0 plus 0.001 minus minus cosine of 0 divided by 0.001, right? And like whatever that ends up being, I mean, like that will give you something close to 1. In fact, it's possible that if you put it on the calculator, it would just give you 1 or like 0.99999, depending on how the calculator like rounds up everything. But the important thing is like, whatever this quantity is, the way it differs from the true value, which we know the derivative of cosine, like, the derivative of cosine would be, I mean, I should have used like maybe sine so that you would, let's use sine so that you get something that should be 1, not 0, just for fun. So, like the derivative, that the derivative of sine is cosine, so this should be like, this should be cosine of 0, which should be 1. And like whatever like this gives you is close to 1, but the idea is like how much it differs should be depends linearly on h. So it should be like, it's like that's what O of h means. Like, the dominant term is like depends on h. Is that okay? Is that making sense so far, so good? Now, the cool thing is that, and this is kind of like the interesting part, this is not the best way that you could use to approximate the derivative. So there are better approximation schemes, which just use in more clever ways Taylor's formula. Okay, so let me show you another approximation scheme. So, and this is actually an improved one, and you'll see why it's an improvement. So here's like a different approximation scheme. So again, what I'll do is take Taylor's formula. Let me copy paste it. Hmm. By the way, I should make a picture here. So in terms of a picture, like, on the number line, what's going on? Let me see if I can make this picture here so that, it's less confusing what I'm about to do. But in terms of a picture, what's happening is that you have the real numbers, you have the number line. Here you have the number A, right? Here you have A plus H. So usually whenever you deal with this, you're thinking that H is positive, like like that's kind of like the usual convention, when you're drawing things on the line or whatever. So like kind of like that's why this is called like forward difference, because the forward difference is like approximating the derivative using A and the point A plus H, which is forward, like a little bit after A. Um, the the next approximation is kind of like also, a bit more symmetric. So you will consider also A minus H. Okay. So you can also, like you can also apply Taylor's formula to find f of A minus H. It's kind of like the same idea. The only difference is like because now there's like a minus here, a minus H, because there's a minus H here, you can, wherever you see an H, you just replace it with minus H. So you get f of A minus f prime of A times H plus 1/2 f double prime of a times h squared. Like this one doesn't change in sign because h and minus h squared to the same thing, but the cubic does change. So this one gives you minus 1/6 f triple prime of a h cubed. And then again, the well, like again, like the O is just like a symbol to say that whatever comes next, the dominant term is h to the 4. So again, the constants per se don't matter too much. So you can also continue writing of h to the 4. Okay. So now you have like these two Taylor formulas applied. At, one is for a plus h, and the other one is for a minus h. Okay, and there are these two equations. This is what's interesting here is that if you were to add them, right? What happens if you add them? If you add them, then these derivatives go away, right? They cancel because they appear with opposite signs. So there's no way, if you were to add the equations, there would be no way to kind of like find anything interesting about the first derivative because you kind of like cancel it out. So the alternative to adding them is subtracting them. So what you can do is like f of a plus h. So you do f of a plus h minus f of a minus h. Okay, and what is that going to be equal to? So now, when you subtract the equations, when you subtract this one with this one, now these two cancel because they have opposite signs, right? When you subtract this one with this one, like, the minus becomes a plus, so you get 2 times f double prime of a times h, right? Then when you subtract these two, they cancel again because, you know, they cancel because they come up with the same sign, right? And then when you subtract these two, they contribute, right? Because the minus flips it. So you get you get 1/3 f triple prime of a times h cubed. And again, like that's why I'm saying like the big O notation, these big O notations don't cancel, right? That's not how they work because like you don't know what the coefficients are. So you just say that it still depends on O of h to the 4. So you don't subtract big O's, like the big O's just remain being big O's, basically. Is that making sense how I got this equation? And so now this is interesting because what happens if, you know, what happens here if you try to solve for, again, everything has an h here, so let's divide by that. Let's also divide by 2. So you would find that f of a plus h minus f of a minus h divided by 2h is f prime of a plus, okay, if you divide by 2, you get 1/6 f triple prime of a. There's an h that drops, right? Because you're dividing by h. So you get h squared. And then again, like dividing by 2, there's no point in putting big O divided by 2. That like is not useful. But it is useful to say that you drop the dependency by 1 power of h. That is important to keep track of. So this actually becomes big O of h cubed. Okay? And all of this, right? All of this, what is all of this? This is big O of h squared. So interesting, and this is another way to approximate the derivative. This is called the central difference approximation. So basically in this method, right? So what is the central difference approximation? It's just to say that f prime of a is f of a plus h minus f of a minus h divided by 2h. plus, like again, like you kind of like are moving this to the other side, but when you move it, like it still remains big O of h squared. So plus a big O of h squared. So this is another approximation for the first derivative. Um, but what I want you to notice here, right, is that what's interesting about this central approximation is that it is an improvement on the previous one, right? This is better, right? Why is this better? Because the error term, this is how you should think about this, because this is like whatever the difference is between the derivative and the approximation, right? So this is the error term. The error term here is O of h squared, whereas in the first scheme, the error term was O of h. Because h is small, O of h squared will be smaller than O of h. So what this is saying is that this is actually, in terms of convergence, this like approximation kind of like it is better than the previous one. So it would give you a better result, like a better value for the derivative. So this error term is smaller than the O of h. So this is smaller than O of h. So it converges, if you thought about creating like a sequence, by taking a sequence of values for h that go to zero, so this would kind of like converge like faster to the value of the derivative. So this approximates the derivative better. Is that okay? So far, so good? Is that making sense? Okay, so why, like, okay, this is interesting, but how is this related to the polynomial stuff that we have been discussing so far in the course? So, like, we had the question, but like, let me at least just mention some of this today, and then I'll wrap it up tomorrow. But how is it related to polynomials? So, how is it related? Well, here's one way to think about what's going on. So you had 3 points, right? Um, or you had three values for x, with which were a plus, sorry, a minus h, a, and a plus h, right? So those are like the three x values that we're working with, and you could think about like three data points, which are a minus h, f of a minus h, then a comma f of a, and then a plus h comma f of a plus h. Okay, so you have three data points, and so you could think about finding the Lagrange like now we do go back for a second to Lagrange polynomials. So, or like the Lagrange interpolation. You could try to find the Lagrange polynomial that passes through these points, right? Since it's 3 points, like you want to find a degree 2 polynomial, right? So you try to go, you will find the Lagrange polynomial. Like kind of like in the same way we were doing it in the first exam, for the first exam, passing through a minus h, f of a minus h, a comma f of a, and a plus h, comma, f of a plus h. So this is like a fun exercise. Like, I mean, I'll just write down the formula, but it's not doesn't take too much time to kind of work it out because it's only 3 points. Okay, so if you write down the expression, okay, the polynomial that you get, you can check if you want that the polynomial that you get of degree 2, and so it's going to be a parabola, would be f of a minus h times x minus a, x minus a minus h divided by 2h squared plus f of a times x of a, x minus a plus h, x minus a minus h divided by 2h squared plus f of a plus h, x minus a plus h times x minus a times 2h squared. Okay? Like I'll put it as an exercise if someone wants to work it out because like it's like a fun calculation to do. So you get this polynomial of degree 2, right? It's a quadratic polynomial. It depends on x squared, as you can see here. Okay? And what's interesting here, what's interesting about this polynomial, and again, like I'll put it for you to check it out, but you can check that if you take the derivative, the first derivative of this polynomial, if you take the derivative of this polynomial and evaluate it at x equals a, you will find this thing. You will find this expression. Okay? You just take the derivative with the product rule, plug x equals a, and this is what you will get. But what's interesting about this expression, this is precisely, what is that formula? What is that? That is the same quantity that appeared here in the central difference approximation, right? So this is like, the approximation. This is the same formula. This is the same as the formula for f prime of a coming from the central difference approximation. So what that means, like if you kind of think about it for a second, what that means is that if you want to estimate derivatives, at least in this case, the way we were trying to estimate derivatives turns out to be equivalent to finding the Lagrange polynomial and finding the derivative of that Lagrange polynomial. So what that means is that the polynomials, like these interpolating polynomials, can be a good way of approximating the derivatives, and they will also be and turn out to be a good way to approximate the integrals. Like they kind of will work equally well for both. And so what we will do tomorrow is kind of discuss and discuss how you can use these polynomials to kind of like approximate derivatives uh, using the fact that you can express the polynomials as a combination of like Chebyshev polynomials. So the Chebyshev polynomials will be useful in for a reason I'll explain tomorrow. But this is kind of how it all starts connecting with like everything else in the course. Like, like the course is kind of like, in a sense, that they are a bunch of different topics, but there is some connection between them. And now, like some of these connections are started to kind of like start like manifesting themselves. So like they are not like completely independent of one another. But I'll tell you more about that tomorrow because like that way I do want you to have like time to work on the quiz. So yeah, if you let me make it available. So now you can take the quiz. And unless you want to ask me something before you take the quiz, I'll just stay here until